And yeah, use the playlist. That's what I like. Okay, chemistry 1411. So we're going to back up a little bit here, and I want to review change in pressure with you because we talked about this at the end of the last lecture. And we talked about ways that we can affect the change in pressure in a reaction. It says here there's several ways to change the pressure of a reaction when you have one or more gaseous components. So you notice that when you're talking about pressure, you're going to be talking about gases, right? This doesn't apply to equilibria that involve only solids, liquids, or aqueous solutions. We've got to have gases, and we looked at kind of two overall scenarios. The first one is, or the first two are for a constant volume system. So that's where your container is rigid. You can either add or remove a gas, or you can add an inert gas. And I told you the answer to the inert gas is always really simple. There's no change in K. And then another option is to change the volume of the container. And we'll look at some problems today that involve changing, like literally changing the size of a container, making it smaller, making it bigger. How does that affect Q? And again, these are reactions with gaseous components, which you want to keep in mind. Anyhow, so let's review here. It says constant volume systems. It says increasing or decreasing the partial pressure of something in a reaction. It's got the same effect as increasing or decreasing concentration. And we already talked about that in detail, right? We looked at that a lot last class. And if you're wondering, well, how do I know that pressure and concentration are directly related? Well, that's comes straight out of PV equals nRT, right? We can solve that for N over V. And if you don't understand what's going on here, look, I'll just go over it really slowly. You have PV is equal to nRT, ideal gas law. So you have pressure is equal to N over V times RT, right? And N over V is the same thing as concentration. So therefore, you can see that pressure and concentration are proportional to each other. Now, as I told you, the addition of an inert gas, if you throw an inert gas in there, it increases the total pressure, but it doesn't change the concentrations of anything. And so the answer, whenever you see any kind of question about throwing an inert gas in a reaction, is not going to do diddly squat to the equilibrium. Okay, so really easy questions whenever you see the inert gas. And if you're wondering, what's an inert gas, Mr. Dion? An inert gas is nothing more than a gas that's unreactive. So something like helium, right? It's a noble gas. It's highly unreactive. Neon, right? Those are unreactive inert gases. Anyhow, and the volume, I'm not going to read through all this with you, but we looked at this reaction here, the one that I just erased the yellow circle around, and we looked at this example and we said, okay, what would happen if we changed the volume of our system, right? If we made it smaller or bigger? Well, if you examine this reaction, you can see that everything, the nitrogen, the hydrogen, and the ammonia, everything is in the gaseous phase. And so on the left-hand side of the equation, right, the stoichiometric coefficients are 1, 3. 1 plus 3 is 4. Therefore, as far as my reactants are concerned, I have a total of 4 moles of gas. Whereas on the product side, I have 2 moles of ammonia. Therefore, I have 2 moles of gas. So if we go back to the ideal gas law, and I'm not going to review that, that's general chemistry 1, but which one of these sides would take up more space? Right, the side with the more number of, or the greater number of moles of gas is going to need more room. So therefore, what it's saying here in this example down here, it says, what happens if you decrease the volume of the container? Will the equilibrium shift to the left or will it shift to the right? And the answer is it's going to shift to the right if we decrease the volume. Why? Because there's less moles of gas. It's going to take up less space. Conversely, if we were to, and this example isn't shown here, but if we were to expand the container, right? If we were to make it bigger, what's it going to do then? Well, it's going to seek to fill up that space, so it's going to shift to the left, right? And if you're thinking, you know what, Mr. Dion, that's pretty easy. All I have to do is look at the number of moles of gas. Greater number of moles is where it's going to go if the container is bigger. Smaller number of moles of gas, that's where it's going to go when it's smaller. Yes, that's the answer. Now, if you're very astute, you might be wondering, well, come on, Mr. Dion, what's going to happen if I have the same number of moles of gas on both sides? All right, let's say you have 2 moles of gas reactants and 2 moles of gaseous products. Well, that means that in that case, changing the volume isn't going to change anything, right? It's not going to change. It's not going to change the equilibria one way or the other. All right. Well, there we go. With all that in mind, let's take a look at question number 21. I've made some notes here somewhere. Where are they? Right here. Okay. Number 21. It says consider the following reaction. You have nitrogen plus 3 moles of hydrogen gives you 2 moles of ammonia. If you read our book in detail, you notice this is called the Haber-Bosch process. Anyhow, they talk about it. There's even a beautiful figure in the book that explains, how they make ammonia. Anyhow, it says, using a comparison of Q and K, determine the direction in which the reaction will proceed when the volume of the container is doubled, right? If that's making it bigger, right? So bigger, or if it's halved, that's making it, half the size, so smaller. Well, let's take a look here, and I've already started this work over here. I just rewrote the reaction. So here's the reaction. I wrote down the expression for the equilibrium constant on the right-hand side here. And let's take a look at what would happen if we were to decrease the volume. So A, I'll call that, oops, not a highlighter. Come on, Mr. Dion. There you go. Okay, so A, let's say we'll say volume is doubled. Okay? If the volume is doubled, that means the concentration of everything is going to be a half as much, right? If you take, I don't know, I can't come up with a good example off the top of my head. Let's say you have some, I don't know, Coca-Cola or coffee. Let's say coffee, okay? You have some coffee, and then you add double the volume of water, right? So you add the same volume again. The coffee is going to be weaker, right? It's more dilute. So when volume is doubled, the initial concentration is going to be divided by a half, right? We're going to have a half as much. Now, if we think about our equilibrium expression over here, if we think of everything as starting out as an initial concentration of 1, so you have 1 squared divided by 1 times 1 cubed. Hopefully you can do that in your head, and that means your K would be equal to 1. So if we change everything to a half, right, we divide everything in a half, we get our Q is going to be equal to 1/2 squared, son of a gun, there we go, divided by 1/2 times 1/2 to the power of 3, like that. Now, if you punch all that spinach, that equals 1/2 to the power of 2 divided by 1/2 to the power of 4, which equals 1/2 to the negative 2, which is equal to 4. You could just do this in your calculator, or you could do it in your head. Doesn't matter. Either way it works. But therefore, we see that Q is greater than, oops, not 1. Q is greater than K. Q is also greater than 1. But our Q, right, here's our Q. We just calculated it. It's greater than our K. What does that tell you? It tells you the concentration of the numerator is higher. So therefore, what's going to happen? The reaction is going to go in reverse. Let's write that down. Reaction goes in reverse. Okay. Now, if you're thinking, Mr. Dion, what are you doing? What is up with all the math? You didn't even have to do that. Why are you wasting my time? Hold on. Sometimes it's nice to show your students, more than one way there's more than one way to skin a cat. There's more than one way to solve these problems. If you're thinking, Mr. Dion, all you had to do was this, man. Look, you got 4 moles of gas on this side. You've got 2 moles of gas over here. If the container is bigger, it's going to shift to this side, right? It's going to shift to the reactants. Well, there's nothing wrong with that rationale at all. I taught you that, okay? So either way it works, but the question actually asks us to compare Q and K. Now, if you're wondering which way is right, they're both going to work. Okay, they're both going to work perfectly well. I'm just showing you the mathematical proof. That's all. Let's try the next one, and I'm sure you could all probably do it faster than I can. Same rationale, but now we're going to say the volume is halved. Okay. Now, come on. If you're saying, well, Mr. Dion, it's going to be a smaller container, it's going to shift to this side, right? There's less moles of gas. Yes, I know it's going to go towards the products. Well, let's prove it mathematically. All right. If the volume is halved, that means the initial concentration is going to be multiplied by 2. All right. So maybe I'll just erase that, and I'll call it 2 times the initial concentration, like that. Well, let's calculate our Q. So that's going to be 2 squared divided by 2 times 2 cubed. So that's 4 over 16. Yeah. So that's going to equal 1/4. Okay. So that's going to be equal to 0.25. Okay. Or 1 over 4. Same thing. Anyhow, so we get that Q is less than K in this case. And so our reaction goes forward. Right? If the Q is too small, right? The Q, 0.25, is less than 1, right? So that tells us that our denominator is too large, right? And it's going to have to shrink. Therefore, we're going to have to go towards the products in the forward direction, okay? Give me a thumbs up if you follow me on that. You're like, Mr. Dion, I probably won't do the mathematical proof on an exam for myself, for my own personal edification, but I think I might just, look at the number of moles of gas and figure that out, okay? And there's nothing wrong with that at all. Either way works. All right, well, let me show you something before we look at a more involved problem. Just let me find where I was here in the slides. Give me 2 shakes of a lamb's tail here. I just wanted to show you number 22 quickly. Didn't want to spend a lot of time on number 22. I don't even know if there's room for it here, but let me just show you. If you had to do the same thing for this reaction, okay? The number, or A gas is in equilibrium with B gas. So that means, let's just write the equilibrium expression here. K is going to be equal to B over A. Now let's imagine the initial concentration of everything is 1, then our K would be 1. Okay, so if we do the same thing, so if we start with doubling it, so doubled, right? If we double the size of the container, that means it's going to be the initial concentration divided by 2. So that means our Q is going to be 1/2 divided by 1/2, which equals 1. So what does that mean? It means that Q is equal to K and no change. Okay, no change in the equilibrium. Right? It's not going to go forward. It's not going to go backwards. If we try the same thing over here when it's halved, if it's halved, that means it's going to be 2 times the initial concentration. So that means that Q is going to be equal to 2 over 2, which equals 1. So that again means Q is equal to K, so no change. Now I went over that really quickly, but I'm sure that most of you understood what was going on before I even, started solving the problem. You said, whoa, whoa, whoa. Look, I have the same number of moles of gas on the reaction side and the product side. Of course there's not going to be a change in direction, right? You told me that when delta N is 0, when there's no change, there's not going to be any change in Q if I change the volume of the container, okay? Let's take a look at the next one. This is a good question. Just a bunch of different, scenarios here. And you can see how this would loan itself to easily to a multiple choice kind of thing. Question 23, just have some things here in a table. Let's see here. Let's just see if we can solve these qualitatively. Just looking at the reactions, looking at the changes, and see if we can determine which direction the equilibrium is going to shift. So here we are. We're really, in question 23, we are using our wits, our knowledge of Le Chatelier's principle to solve some problems. So let's start with the first one. It says you have dinitrogen tetroxide in equilibrium with 2 moles of nitrogen dioxide, and you increase the pressure by adding nitrogen dioxide and maintaining a constant volume. Could anybody tell me, will the reaction shift, we'll call it left or right? Will it go left or right? Absolutely. Thanks, Sierra. Sierra's got it. Oops. I don't have a right pen here. Yeah, it's going to shift to the left. Right. All Sierra said was this. She said, look, Mr. Dion, you're increasing the concentration of the product. So in order to reestablish equilibrium, your Q would be too high in this case, right? It'd be higher than K, so it has to shift towards the reactants to reestablish equilibrium. Let's try the next one. What would happen in the second one? You have sulfur dioxide plus 1/2 mole of oxygen producing sulfur trioxide. What would happen if you increased the volume of the container? Would it shift to the left or the right? Yeah, exactly. Yeah, it's going to shift to the left. Why is that? Because if you look at the number of moles on this side, I have one. I can write the number 1. Come on. 1 plus 1/2. So you have 1.5 moles of gas on this side, and you only have 1 mole of gas on this side. So if the size of the container is increased, it's going to shift to the side with the greater number of moles of gas, right? I just plainly have more moles of gas on that side. Exactly. Thanks, Violet. Perfect. Let's try the next one. This one's, I'll just throw it out there to my students. It says here, increase in pressure by adding inert helium gas and maintaining the volume. What happens there? What happens here in the third one? Nothing happens, right? When I add an inert gas, diddly squat happens. Nothing happens. So we'll put here, oops, no change. All right, no change there. Let's take a look at the next one. You have graphite plus steam gives you carbon monoxide plus hydrogen. And what do? You decrease the volume of the container. You make it smaller. Will it shift to the left or to the right? And this one, where will it go? It's not nothing. No, it's not nothing. Look carefully. Yeah. So if I decrease the volume of the container, no. If I make it smaller, it's going to go to the left. All right, let's take a look. Here's the equation. You got carbon in the solid phase plus steam in the gaseous phase, which is in equilibrium with carbon monoxide in the gaseous phase plus hydrogen in the gaseous phase. On the product side, you have 2 moles of gas, and on the reactant side, you have 1 mole of gas. Graphite is a solid, it's not a gas. So if I'm decreasing the volume of the container, it's going to shift to the side with the least number of moles. It's going to go to the side that takes up less space. So this one's going to shift to the left. Le Chatelier's principle, right? Okay. If you're unsure, if you're like, I need to read more about this, Mr. Dion, it's on here, right here. Non-constant volume system. Okay, so I'm not going to go over it again. Let's keep looking here. What about, okay, let's go to the next one. So now I'm looking at this one right here. Nitrogen plus oxygen gives you 2 moles of nitrogen monoxide. What would happen there if I increased the volume of the container? I made it bigger. All right, no change. Zilch. No change. Okay, and the last one says here, you remove solid calcium carbonate, assuming the volume of calcium oxide is negligible. No change. Yeah, if you remove a solid, it's no change. So we'll put here, where's my green pen? There we go. No change. It doesn't say that we remove all of it. It says we remove some of it. Okay, so it's not going to change the equilibrium. All right, because the solids aren't part of the equilibrium expression. There you have it, folks. Who feels a little bit better now? Like, I don't think I'm understanding this Le Chatelier guy. He was pretty smart. Yeah, he was. He was a pretty intelligent cat. All right, good, good. Well, in that case, I want to try another problem with my students. And this one involves Le Chatelier's principle. So we got to really put on our thinking cap. I'm going to let you guys read the question. I forgot to bring water into my office, and my kids turned the heat up. So just give me a second here. I need a drink of water. All right, let's take a look at 24. Got to read these questions carefully. It says you got a flask, a 4-liter flask at equilibrium. It contains 0.2 moles of dinitrogen tetroxide, 1.6 moles of nitrogen dioxide, and it reacts according to this equation. The volume of the container is then increased to 8 liters, right? So it's doubled. The size of the container is doubled. Don't ask me about these fonts. I go from a capital L to a cursive lowercase. I don't know what happened there. Anyhow, how many moles of each gas will be present when a new equilibrium is reached? I have a question for you first, okay? can you calculate K with the information that's given? Could we calculate K? Just yes or no? Yeah, absolutely we can, right? Violet says we can, and we absolutely can. Why? Because it tells you the volume, and it tells you at equilibrium how many moles of everything you've got. So we can calculate K from this, no problem. First, we can start by writing an expression for K. Here's our balanced equation. I'm not going to rewrite it yet because I'll need it for the ice table. But we have K is equal to the concentration of NO2, excuse me, squared, divided by the concentration of dinitrogen tetroxide. Perfect. Okay, let's plug in our concentration. So we have 1.60 moles of our nitrogen dioxide divided by 4.00 liters. And we're going to square that. We're going to put that over our 0.200 moles over 4.00 liters. Okay. Anyhow, you punch all that in your calculator, you end up with 0.400. I'm leaving the units out because, again, K is a unitless number, divided by 0.0500. And you end up with a K C, which is equal to 3.20. Okay, so now we've solved for our KC. And now what we're going to do is we're going to increase the volume to 8 liters, right? We're still going to have the same number of moles. We're still going to have 1.6 moles of NO2. We're still going to have 0.2 moles of N2O4, but we've doubled the size of the container. So we can calculate their concentrations, right? Their initial concentrations. Let me show you how. If you're unsure, let's make an ice table. So we have N2O4, the gaseous phase, is in equilibrium with 2 moles of NO2 in the gaseous phase. Pen back. There we go. So for N2O4, we've got 0.200 moles divided by 8.00 liters. I know that many of you can do the math in your head. That's cool. Yeah, 1.60 moles divided by 8.00 liters. So that means that our initial concentrations are 0.0250 molar and 0.200 molar. Now, I could calculate Q at this point if I wanted to, but that would involve more calculations when I don't need to do that. I know that if the container is getting bigger, right? If the container size is being increased to 8 liters, that means the size is doubling. Who could tell me which way the equilibrium would shift if I'm doubling the size? Is it going to shift to the left or to the right? It's going to shift to the right. How do we know that? Because there's more moles of gas on this side. It's going to shift to the side that's going to take up more space, right? We have a bigger container. It's going to seek to fill up that container, okay? So we have 2 moles of gas over here, and we only have 1 mole of gas over there. So again, since the size of the container is being increased is larger. That means the shift is going to shift to the left because more moles of...
You mean shift to the right, right?
Yeah, sorry, shift to the right. Yep. Because more moles of gas. Yep. There we go. Because more moles of gas, and this is Le Chatelier's principle. Okay, so you need to understand non-constant volume systems and what's going to happen if you change the size of the container. All right, so that means if the equilibrium is going to shift to the right, that means that for our change, we can write that here we're going to have plus 2x, and here we're going to have minus x, like that. Now when we write our equilibrium, here we have 0.0250 minus x, and here we've got 0.200 plus 2x. Now all we have to do is solve for x to find the concentration at equilibrium. Kind of running out of space here, but I'll go for it. We've got our equilibrium constant 3.20, which is equal to this 0.200 plus 2x, and I have to square all that divided by 0.0250 minus x. So this is going to end up being a polynomial and we have to solve the quadratic, you end up with 0.0800 minus 3.20 x is equal to 0.0400 plus 0.800 x plus 4x squared. And then you solve that for 0, and you end up with 0 is equal to negative 0.0400 plus 4.00x plus 4x squared, of course. And then I use my calculator to solve this. I mean, you can use the quadratic formula if you want. I'll include it on the cheat sheet, or the handout is the correct term for it. Anyhow, again, in my calculator, which is a TI 36 Pro, if you go into the polynomial function, so poly solve, and you just put everything in there. You put the 4 in for your A, and then enter. I'm solving it right now. And then you put a 4 in for your B, and then for your C, you would put negative 0.04, and then you go solve. And the first number that comes up is I get the x is a positive number, and that's the one I want, is 0.0099. Like that, so 990. And that would be the change in concentration. So now if I want the concentrations at equilibrium, all I have to do is plug x into both of these, and I get that the concentration of N2O4 is equal to 0.0151 molar, and the concentration of NO2, right? And if you're wondering where I'm getting that number, right, all I have to do is take 0.2 plus 2 times this number, and I end up with the concentration of NO2, and it ends up being 0.220 molar. And there you go. That's the answer. So you got to be able to use the quadratic formula, but I know all of you have used the quadratic formula at some point in your life for sure. So there you go. A little bit of practice, solving quadratics, looking at Le Chatelier's principle. But it seems to me that just by looking at some of the answers that I'm getting in the chat, I want to be sure that we 100% understand which way the equilibrium is going to shift based off of the information, right? Because if you don't get this part correct, even if you did, you were a math expert, if you don't get this part correct, you're never going to get the question right, okay? So let's think about this. On the product side, we have 2 moles of gas. On the reactant side, we have 1 mole of gas. Let's go back to General Chemistry 1 for a few minutes. We have PV is equal to nRT. And if we solve for volume, we have nRT over P. We're talking about this reaction, right? That's at equilibrium. We're not talking about change in temperature. We're not talking about change in pressure, right? And we're not talking about change in R, because R is a constant. That tells you the volume is proportional to the number of moles, directly proportional. If the number of moles goes up, the volume goes up. If the number of moles goes down, the volume goes down. That is something that we learned last semester if you were in my class. So if we, again, look at this reaction in detail, you can see the product side has 2 moles of gas, and the reactant side has 1 mole of gas. So if I'm making the container bigger, it's going to seek to fill up that volume, right? To fill up that space, okay? And if it wants to fill up that space, it's going to have to go to the side that's going to take up more space. Conversely, if I squeeze it, right? What if I try to shrink everything down, right? And put it in a small container? Well, the molecules are going to be like, holy hell, this isn't right, right? We're not at equilibrium. We want to take up less space. So they're going to shift to this side in order to take up less space, because 1 mole of gas takes up less moles of space than 2 moles of gas based off of PV equals nRT. Give me a thumbs up if you're like, I think I got it, Mr. Dion. Just give me 4 more hours alone. Cha-cha. All right. Ideal gas law. Well, let's look at the last 2 catalysts. We can do that really quickly. Let's talk about change in temperature, right? Because we've been talking about a change in pressure doesn't affect K, change in volume doesn't affect K, right? We're not talking about affecting K. We haven't, our K's never changed, right? But something that we talked about earlier on was that K is affected by temperature, right? A K is constant at constant temperature. So what the heck happens when you change the temperature? I guess it gave myself more room here. Well, let's talk about it. The equilibrium constant, right? Our capital K, big K, of a given reaction depends on temperature only. So if you change the temperature, you're going to change the K. That's it. Now, thermal energy. You guys remember endothermic and exothermic reactions? Right? An exothermic reaction, I think that's more intuitive. You have exo, sounds like exit. So an exothermic reaction is one that releases heat. Heat is exiting. An endothermic reaction is one where heat is entering the reaction. So if you think about that, and again, we looked at that in General Chemistry 1, you can view the heat as a reactant or a product, right? Think about it. In an exothermic reaction, you're releasing heat, so heat's a product. In an endothermic reaction, you're putting heat in, so heat is a reactant. And therefore, let's say you have this reaction, this chestnut that just won't leave us alone, right? This reaction right here. You can see that this is an exothermic reaction, exothermic, right? Why? Because heat is being released. You're doing this reaction, but heat is a product, okay? So what happens is that you can treat this as a product. You treat heat as a product. So that means, let me delete all this spinach, okay? That means that if we were to increase the heat, right, we crank heat up, that means we're increasing this. And then we're going to shift to this side to balance it out. Now, if you're wondering, like, what about an endothermic reaction, right? What if I, removed heat from an endothermic reaction? Well, that would shift it towards the left as well. But we'll look at all the different scenarios. All right. Anyhow, this is just kind of a point that I wrote down here. I think I'm paraphrasing something that's in our textbook, which is this, that Le Chatelier's principle, it can't tell you the size of the change in K, but you can predict the direction of the equilibrium, right? And that's one of the main skills that you're developing right now, right? I think my students are getting a little stronger at predicting changes in volume, inert gases. So now let's see if we can, sink our teeth into some problems that deal with changes in temperature. Oops. Give me 2 shakes of a lamb's tail here. And we'll look at question number 25. All right. So let's see here. We got a couple of reactions. Let me start it slow, you guys. 25I, or 1 here, you got N2O4 in equilibria with 2 moles of NO2. We have delta H is equal to 58.02 kilojoules. Could anybody tell me, is this reaction, the first one, the one I have the yellow highlighter next to, is that an endothermic reaction or an exothermic reaction? Based off of what you learned last semester. No, it's not exothermic. This is an endothermic reaction. Okay, so this is an endothermic reaction. When our delta H is positive, it's endothermic. When delta H is negative, it's exothermic. All right, so if you have to go back and review your change in enthalpy, do that, okay?
So does delta H mean when it's positive, that means it's releasing energy?
No, it's the opposite. When delta H is negative, that means that overall the reaction is releasing energy. All right, so when delta H is positive, this is endothermic. When delta H is negative, this is exothermic. All right, so if you want to, no, it's not counterintuitive at all if you understand the formula. So go back to your general chemistry and look up the formula for change in enthalpy. All right, so let's take a look at these reactions at 25 degrees Celsius and answer these questions. So the first one is an endothermic reaction. All right, and it says the temperature of this reaction is increased to 900 Kelvin. Now we're starting out at 25 degrees Celsius. 25 degrees Celsius is 298 Kelvin. All right, so let's see here. If we have A, our reaction, we have 58.02 kilojoules plus N2O4, which is a gas in equilibria with 2 NO2 in the gaseous phase, right? That's our reaction. Again, it's endothermic. We're putting heat in as a reactant. Let's see here. If the temperature is increased, it's asking us, and we'll put here if T increases, what's going to happen? Will the reaction shift towards the products or the reactants? Could anybody tell me? You increase the temperature. If temperature is regarded as a reactant and we turn this up, right? If we crank this up, that's what we're doing. What's it going to do? Right? It's going to shift it towards the products to try to alleviate that strain, right? What's Le Chatelier's principle? You have a system at equilibrium, you place a stress on it, the system is going to shift to whichever side it has to eliminate that strain or to alleviate that strain or however you want to phrase it, right? So if the temperature is being cranked up, the Kp, put here Kp, one of my blue pen, Kp, and here's our Kp right there. Let's just put here, let's make it simple. A reaction will shift to the right side. Okay, there we go. Okay, let's see. What would happen if we were to decrease the temperature? If the temperature is decreased, think about it in terms of concentration. If you were to lower this, right, pull heat out, then the reaction is going to shift towards the left to recompense that, right, to make up that loss of heat. So reaction will shift to left-hand side. Okay, and if we look at the second one, so this is A. I did it all in blue. Maybe I should have called these 1 and 2. Whatever. There we go. So scenario 1 and scenario 2. Anyhow, so let's look at the second one. We have this reaction. It's exothermic, right? Heat is being released. You have 2 SO2 in the gaseous phase plus O2 in the gaseous phase is in equilibrium with 2 sulfur trioxide plus 198 kilojoules, right? Heat is a product, exothermic reaction. If you're decreasing the temperature, so if T decreases, could anybody tell me which side this would go to, would shift to? Would it shift to the left or to the right? This specific case, it's going to shift to the right. Exactly, because I'm removing heat. If I drop that down, it's going to shift to the right to balance out that change. Right, so shift to right. And then if the temperature is increased, it's going to shift to the left. Right, shift to the left, right? Because then I'm changing this, I'm raising it up, so it has to go in this direction to make it up. And that's it. There you go. Le Chatelier's principle with respect to temperature. Okay, let's see here. And the last thing we're going to look at is catalysts. Now we talked about catalysts in the chapter 12, where we talked about equilibria, right? In chapter 12, we talked about catalysts, I don't know, for a while, right? In the chapter that deals with reaction rates, we talked about it. And we said that a catalyst does increase the rate of a reaction by decreasing the activation energy, right? Here's an uncatalyzed reaction. And then when you put a catalyst in, not only does it change the mechanism oftentimes, but it lowers the activation energy. And therefore, the activation energy, when it decreases, the reaction is just going to go faster. Simple as that. However, right, that's small k. In chapter 13, which is where we are right now, we're talking about big K. This is equilibria. This is rate, that's speed. This is equilibria. This is how much product and how much reactant is present when the reaction is equilibrium. So if we add a catalyst, sure, the reaction might go faster, but it doesn't change the relative energy of the products and the reactants at all. right? So adding a catalyst, even though it might speed up a reaction, it has no effect on equilibrium whatsoever. Okay, so you have to understand that when you add a catalyst in chapter 12, yeah, it can speed up a reaction, but when you add a catalyst in chapter 13, it doesn't change big K at all. Why? Because again, and I'm repeating myself, the relative energies of the products and the reactants remain the same. It's the transition state that's going to be different, okay? The pathway that's different. All right, so that's kind of a big concept. And I know to some people it might seem simple, it might seem intuitive, but to other people it might take them a little bit longer. But look, let me tell you something right now. When you step into the final exam in this class, and you step into your next exam, you want to be sure that you understand the difference between little k, and maybe I should make this k smaller, I don't know. You need to understand the difference between lowercase k and uppercase k. Chapter 12 and chapter 13. Reaction rate, okay, which is kinetics, and then equilibria, which deals with thermodynamics. All right, two very different concepts. Well, let's take a look at question 26 and 27, which maybe we'll just do 26 for now. Same rationale here. If we look at this reaction, it says consider the following reversible reaction. You got 2 moles of sulfur trioxide in equilibrium with 2 moles of sulfur dioxide and oxygen. My delta H is 198 kilojoules. Could anybody tell me, is this an endothermic or an exothermic reaction? All right, this is an endothermic reaction, right? When delta H is positive, it's an endothermic reaction. So let's write down the reaction. Since it's endothermic, heat is a reactant. 198 kilojoules plus our 2 moles of sulfur trioxide is in equilibrium with 2 moles of sulfur dioxide plus oxygen. All right, let's see what's going to happen. So it's asking us what will happen to the what will happen to the number of moles of sulfur trioxide. So they're asking it a little bit different here, but we're asked to figure out what's going to happen with SO3. Let's highlight it. That's our molecule of interest. Okay, so let's see here. If we increase the number of moles of oxygen, right? If we add oxygen, what's that going to do? Is that going to increase the number of moles of sulfur trioxide or decrease it? I'll just throw that out there first. What in the end is going to happen after equilibrium is established? Yeah, it's going to increase the number of moles of sulfur trioxide. So I'll put number of moles of sulfur trioxide is going to go up like this. Now, if you're wondering, why the heck did you say that, Mr. Dan? Why is it going to increase? Let's think about it, right? We have our K, which is going to be equal to SO2 squared times oxygen divided by SO3 squared, like that, okay? But in this case, we're changing the temperature. So our K is going to change. Now, sorry, we're not changing the temperature, we're changing the amount of oxygen. So if this is going to increase, right, if this goes up, that would mean that our K would go up, okay? We'd have a higher Q. So that means the reaction is going to have to shift to the left in order to make more SO3 to reestablish the K. So that tells me that overall, the number of moles of my sulfur trioxide is going to increase. All right, let's take a look at the next one. It says the pressure is increased by decreasing the volume. So here we're decreasing the volume. What's going to happen to the number of moles of sulfur trioxide? Will it decrease or increase? Decrease in the volume, making it smaller. Yeah, exactly. It's going to increase the number of moles of sulfur trioxide. Okay, so the number of moles of sulfur trioxide is going to increase. Could anybody explain it to us? Just unmute your mic and quickly explain, like, how do you know the number of moles of SO3 are going up if you're decreasing the volume?
Because the product side has less moles.
No, it's because the reactant side has less moles.
Oh, yeah,
Right?
that's right.
The product side has 3 moles of gas, but the reactant side has 2 moles of gas. So it's going to shift to the side with the fewer moles of gas because you've got a smaller volume. If it's shifting to this side, that means that this is going to go up. Okay, so number of moles of sulfur trioxide will increase. All right, pressure is increased by adding HE gas, right? What kind of gas is HE? Where would we find HE on the periodic table? HE is helium.
It's a noble gas.
It's a noble gas, right? It's inert. It's one of the most unreactive, if not the most unreactive compound known. So there's no change, or unreactive element known. There's no known compounds of helium, zero. What happens if the system is cooled? What would happen to the number of moles of SO3? Let me give you a clue.
To go up.
If the system is cooled, that means you're going to be removing the heat, which is going to drive the reaction in this direction. All right, so then if it has to go towards the reactants, you're going to increase the number of moles of sulfur trioxide. So we can put the number of moles of SO3 is going to go up. Next one is if a catalyst is added. What happens when we add a catalyst? What will happen to the number of moles of sulfur trioxide? Start messing around with catalysts. Exactly. Zilch. No change. Because a catalyst does not affect K, big K. And the last one is if SO2 is removed. So if we pull all the SO2 out, we start pulling it out, what's going to happen to the number of moles of SO3 in that case?
It should go down.
They're going to drop, right? The number of moles of SO3 are going to go down. Why? Because the equilibrium is going to shift towards the right, right? So when that happens, I'm going to consume sulfur trioxide, so I'm going to have less of it. Well, there you go, my friends. Oops, I didn't mean to delete that. There we go. So that covers change in volume, change in temperature. It covers a catalyst. And again, you can see how these, loan themselves really quickly to questions about, or multiple choice questions, which is the format of your exams. Anyhow, I thought we would take a look at the next one too, which deals with a whole bunch of different equilibria. I'm going to give you a second to look at as many as you can. Oops. All right, so let's take a look at these. And it says determine the response of the equilibrium to the stress indicated. No calculators, right? Don't need it. Don't need anything. Just need your brain and a little bit of thought, maybe a pencil if you want to scribble on a page, but that's about it. So we look at the first one. You have carbon monoxide plus steam gives you carbon dioxide plus hydrogen. That's in equilibrium. Then you add an inert gas to the volume, or to a constant volume container. And it says determine the response of the equilibrium. So we'll call it, left, right, or no change. So we'll say this direction. So we'll say right, left, or no change. There you go. All right, thanks, Katie. The answer is no change, right? We'll call it here, we'll call this the effect. So no change. There we go. Why? Because it's in inert gas. Inert gases don't do anything. Okay, next one, you have 4 moles of hydrogen plus carbon disulfide gives you methane and hydrogen sulfide. And you add an inert gas to a non-constant volume container. Well, the same thing happens. When you have an inert gas, it doesn't change anything, okay? It doesn't change the concentration of anything. So again, we're going to have no change. Why? Because it's an inert gas. Next one, we have zinc phosphate. It's in equilibrium with zinc 2 plus and phosphate. And what would happen if we were to add some zinc phosphate? What would happen to our equilibrium here?
The right.
What's going to happen? Make sure to look at the faces of the reactant and the products. No, it's going to give you no change, right? Because zinc phosphate is a solid, right? It's not an aqueous, okay? It's a solid, so you're going to have no change there, right? A solid is not part of the equilibrium expression. If I was to ask you to write a K for this, write a Kc for this, your Kc would be Zn 2 plus to the power of 3 times phosphate to the power of 2, okay? Your zinc phosphate wouldn't even be in there, so it's not going to change anything. What happens in the next one, though, if we add water to this? This is a good question. What if we add water? No, there's going to be a change. We went over an example like this today. Yeah, I understand that water is a pure liquid. I totally get that. There, does that help? What's going to happen if we add water? Nobody's got the right answer yet. It's going to shift to the right. Right? Why? Here's our Kc expression right here. Right? If we're adding water and these are in aqueous phase, what's going to happen? Their concentrations are both going to decrease. Right? You're going to decrease the concentration of zinc and you're going to decrease the concentration, right? You're diluting it. So the reaction is going to shift to the right to recompense that. Okay, remember this morning we looked at a reaction where we talked about dilution, right, by doubling the size of the container. And then we talked about halving the size of a container. So for adding water, so we're diluting, therefore concentrations decrease, and therefore the equilibrium is going to shift towards the right. Does that make sense? Good. Thanks, Sierra. Good. So it's going to shift towards the right like that. Let's take a look at the next one. We have the pressure of the container being increased. You got nitrous acid in equilibrium with a proton and nitrite. What would happen if I was to change the pressure here? Remember, you got to apply all your chemistry knowledge. Right? Think about everything you ever learned. Get this reaction, and I'm changing the pressure. Okay, let's back up. So, when we change a pressure, okay, what phase has an effect, is affected by changes in pressure? Gaseous phase. If you have a solution in water, is a change in pressure going to change it? No. Pressure has no effect on an aqueous solution. So if you go back here, you can see that everything is in solution. So if we change the pressure, right, the pressure of the container is going to be increased. We're going to have no change because everything is aqueous. Aqueous solution. Okay, nothing's going to change. All right, let's try one that deals with temperature. This reaction here, could anybody tell me, is that endothermic or exothermic? All right, it's an endothermic reaction because you're putting in heat like this. Okay, you're putting heat in, so this is an endothermic reaction. Now, if we increase the temperature, that means we're increasing this. So the equilibrium is going to shift to this side to make it up. It's going to shift towards the products. It's going to shift towards the right. So we'll put towards the right. The next one, could anybody tell me, is this an endothermic reaction or an exothermic reaction? My delta H is negative 905 kilojoules per mole.
Exo.
It's exothermic, right? When it's negative. So if it's exothermic, that means that we can write the heat as a product. 905 kilojoules per mole, like that. Okay, so what's going to happen if we decrease the temperature? If we remove this, which way will the equilibrium shift to make that up? Right, it's going to shift towards the products. So it's going to shift towards the right to make that up. And then lastly, let's see here. The constant, so you have cadmium hydroxide. It's a solid. It's in equilibrium with cadmium aqueous 2+, and 2 moles of hydroxide that's aqueous. And it says that you increase the concentration of hydroxide, or it says OH minus hydroxide is added by adding solid sodium hydroxide to the solution. Who could tell me what's going to happen there? Would it shift to the left or to the right? Yeah, it's going to shift towards the reactants, right? So if you add solid sodium hydroxide in something that's already a solution, what happens when you put sodium hydroxide in a solution, right? If you take solid sodium hydroxide and you put it in a solution, you're going to end up with aqueous sodium cations and aqueous hydroxide ions. So that means the concentration of hydroxide, right, its concentration is going to increase. So if this increases, it's going to have to shift towards the reactants, okay, in order to compensate for that. So it's going to shift towards the reactants. Let me straighten that out. There we go, my friends. So some practice with Le Chatelier's principle. Now 13.4 is a section that's just, I mean, you could sit here and talk about this all day, but I think the best thing that you could do with section 13.4 is to simply practice problems. It says solving equilibrium problems. So the first thing you want to do is have some kind of balanced reaction, balanced equation. You look at all of these problems, they all involve a balanced reaction. Okay. Then you write the equilibrium expression. So you come up with a K. Right. So you come up with a big K. If sufficient information is provided, determine the value of the equilibrium constant at the temperature of interest. So if you've got enough information, you figure out what the K is equal to. So you figure that out. And then you're going to determine, which direction is my equilibrium going to go? Is it going to go to the left or to the right? You've got a number of ways to do that. You can calculate a Q if it's possible. You can use Le Chatelier's principle. Then you would use an ice table, right? We used ice tables a lot with initial change and equilibrium, and we put in some kind of variable X, and we would solve for that. And yeah, we'd solve for the unknown value. And then it says here to check everything at the end. That's something that I don't do with you guys, is once I'm done my ice table, I just get my answer. But if you want to check it out, you can do that for sure. It's really quick to do. All right, so with all that in mind, let's try problem number 28. All right, let's try question 28, and this will probably take us close to the end. All right. So we've got a reversible reaction. A plus B gives you C plus D. Everything is an aqueous solution. They've given us an equilibrium constant. And it says a solution is made by dissolving 0.750 moles of A and 0.750 moles of B and 1 mole of C and 1 mole of D in a 3.5 liter and 3.5 liters of water. Calculate the concentration of each species at equilibrium? Well, I think the first thing that we would do is we would calculate our Q, right? Because we know that K is equal to the concentration of C times the concentration of D divided by the concentration of A and the concentration of B. All right. So we already have our K over here, right? But we can solve for our Q. Okay, so I'll erase that and I'll call this our QC. And we can calculate that from what we're starting with, right? We know the initial concentrations of everything. We know that we've got 1.00 mole of C and D divided by 3.50 liters of water. And we know that we've got 0.750 moles of A and B divided by 3.50 liters of water. And we'll square that. Again, I'm squaring these just because C and D and A and B have the same concentrations respectively. Okay, so when we punch all that spinach into our calculator, and let me grab a calculator, we have 1 divided by 3.5. So we have we end up with 0.286 squared divided by 0.75 divided by 3.5, which gives you 0.214 squared. And then we punch all that in our calculator, we get 1.78. Therefore, Q is greater than K. Now, if this is the equilibrium expression and Q is bigger, that tells me, who could tell me which way my equilibrium is going to shift? Is it going to shift towards the products or towards the reactants? If my Q is greater, right? Thanks, Mackenzie. If my Q is greater, right? Let's break this down again. I mean, if we have this equilibrium expression, I'll go over it really slowly here. Okay, if we have this equilibrium expression, initially we start with 0.805. That's an equilibrium, right? This is our equilibrium, but we know that our Q is equal to 1.78. That tells us that the numerator is big over small, right? We have a number that's too big on the product side, right? If this number is bigger, you've got to have a bigger number on top compared to a smaller number on the bottom compared to the numbers that were used to get this K. Therefore, that means the concentration of these is higher than it needs to be for equilibrium to be achieved. So based off of Le Chatelier's principle, it's going to resist that increase in concentration for the products, and it's going to shift towards the reactants. Does that help a little bit? All right. Give me a thumbs up if that makes some sense. If you're like, Q is bigger than K, yes, it's going to have to shift towards the products, okay? All right, well, there we go. So now we have the initial concentrations, and we have our K, and we know which side it's going to shift to, right? We know it's going to shift towards the left. So let's make an ice table then. Let's rewrite the equation. So we have A in the aqueous phase plus B in the aqueous phase is in equilibrium with C plus D, like that. Okay, so initially we have 0.214 molar here, 0.214 molar there, 0.286 molar here, and 0.286 molar here, right? If you aren't able to solve, using Le Chatelier's principle, using a Q, if you're not able to figure out what's going to happen, then you're not going to get the C part correct, right? And then even if you did all the math correct, you wouldn't end up with the correct answer. And so it's imperative that you understand that the products are going to have to lose concentration and the reactants are going to have to gain concentration. It's minus X and plus X because the stoichiometric coefficient of everything in the equation is 1. So that means that at equilibrium, we have 0.214 plus x. I'm going to leave out the units because we're not going to use them anyway. Plus x, and then we have 0.286 minus x and 0.286 minus x. Like that. All we have to do now is solve for x. Once we have x, we have an expression to figure out what the concentrations of A and B will be. We add 0.214 to it, and we subtract x from 0.286, and we'll know the concentrations of both C and D. All right, so let's plug in some numbers. We have our K, which is equal to 0.805, and that's going to be equal to 0.286 minus x squared divided by 0.214 plus x, and that whole thing is squared. There's a shortcut to get through this one. Okay, just let me make sure I've got this done correctly here. Okay, there's a shortcut here. Could anybody tell me what they would do at this point? I'll throw it out there to my students. What would you do at this point? Would you solve a polynomial or? Anyone? Exactly. Thanks, Violet. So Violet says you can take the square root of both sides. So if we take the square root of this side and the square root of this side, then you get 0.805. Take the square root. Where's my square root button? There we go. So you end up with 0.897 is equal to 0.286 minus x divided by 0.214 plus x, right? And then you rearrange that to solve for x. And then when you solve for x, so solve, we'll just put here solve for x. I'll do this one a little bit quicker. And when you do that, you get the x is equal to 0.050, like that, and it must be molar. So then you plug x into all of these. You get that the concentration of A is equal to the concentration of B, which is equal to 0.264 molar. And then you do the same thing here. You plug that x in here, and you get the concentration of C is equal to the concentration of D. And that is equal to 0.236. 0.236 molar. All right. So there you go. We've covered all of the content in chapter 3 because the rest is just, some practice problems. So what we'll do on Wednesday is I'm going to plan on solving a couple of the practice problems. You can try all of them. I think I put in 10 of them or so. Yeah, there's 10 problems. Try as many as you can. We'll probably go over 2 or 3 of them, or maybe I'll go back and solve some of the problems in the notes. But either way, we'll look at a few practice problems for probably the first, 15, 20, 30 minutes, something like that, maybe 20 minutes. And then the rest of the time, we'll get started with acids and bases. And again, the reason why I want to do that is because the acids bases chapter is definitely the biggest chapter that we undertake. It's a monster. It's a big chapter. All right.